Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Hello, my name is Eileen Rubel, and I'm the Technical Director of Transforming Software Acquisition Policy and Practices here at the Software Engineering Institute. Today, I'm pleased to sit down with Dr. Sarah Sheard. Dr. Sheard is a Principal Systems Engineer here at the SEI. And today we're here to talk about why software architects must be involved in the earliest systems engineering activities. Welcome, Dr. Sheard.
Thank you.
So you recently wrote a blog post on this topic, and it went viral on Hacker News, which was really exciting for all of us. And that's what we're here to really talk about today. But before we get into that, I'd like to do what I call stepping back into my Wayback Machine a little bit. I'd like to get to know a little bit about your background. So you're a systems engineer. Can you tell me how that field has changed since you first entered it?
Thanks, Eileen. I started systems engineering back around 1980, and I was working on satellites. I also have a blog post on how the satellites have changed since then. But in general, I think systems engineering kind of gelled as a field in, I'd say, about the 90s. So a systems engineer from this company or that company would be able to talk to another systems engineer, and they'd be speaking the same language. In that time, of course, software was making this incredibly huge change from something you might write a couple of lines of code for a program to figure out something to the way everything is run. And in that time, the people who were young back when I was young did not work with the software that we have today. And these are the people who are running programs now. So when they were back being systems engineers or in some other engineering field or even managing at that time, the ground floor of what was being done is different from today. And so now that they're managers and at the 50,000 feet level, they're seeing the big picture, but what they have in their head as to how things work is really not the same as how it is working today. The people who are doing software in particular have developed an enormous number of specialties and approaches that are appropriate for today's technical systems, including that idea of a software architect who defines the basic principles behind how software is going to work.
Okay. So let's talk about going back into then defining those rules for how the software is going to work in the system. When the DoD needs a capability, how do systems engineers and acquirers typically determine how that problem should be solved and how that capability really is provided across the system?
Well, that's a really excellent question, Eileen, because somebody has to make the first cut. I mean, we can't take a problem that government's having like we don't have enough resolution on this particular kind of thing, and we would like to have twice as good a resolution, and just throw that at the industry. Instead, the government itself has to decide what is the problem, what kinds of technologies that we have available or that might be available in the near future might help to solve that problem, and how are we going to acquire the pieces of technology so that we can put it together to have the functionality that we need. Somebody up there in government land decides how this system is going to be cut up into pieces that can be then allocated out to this contractor, that contractor, and the other contractor. If you're going to build, a house, you'd probably have a plumber and you'd have an electrician and you'd have somebody working the internet capabilities, the Windows people. We all kind of understand with a house the kinds of pieces you have to cut it into for it to work. But these super new, super high capability programs that have a lot of software content are making new steps. They're really learning a new way to do things. Now, the obvious way, say, and I'm going to go back to the example of the Global Positioning System, or GPS. You've got a satellite up there that is taking pictures and understands where it is with respect to the Earth. You've got ground stations that run the satellite and also provide a lot of data back and forth. And you've got handheld user units, which in this case is my smartphone. And the easiest and most intelligent way to split that up is to have somebody build the satellite, somebody build the ground station, and somebody build the handheld systems. And it seems to be utterly clear and obvious that you should do that. But there's a problem. It worked when the primary difficulty of engineering was in building the thing.
Right.
Okay. Is the satellite going to be stable at this orbit? Is it going to get enough power? And then on the ground station, do we have enough input, output? Do we have computational capability? Is it going to survive through weather, et cetera? And the handheld units, are they going to break? Whatever the hard things about the units used to be the problem. It's kind of not the problem anymore because we have a lot of that down. The bigger problem is the software that provides the continuing capability from yesterday, continuing into tomorrow, but also anything new that is useful to people is generally based on a new kind of software. Now, the software exists because things need to be communicating with each other, and so it's inherently an interpiece of function that the software has to provide. If you're going to do that, you have to watch out that the software isn't split into pieces.
So that seems to sort of set the stage for what kinds of problems we can really have if a systems engineer doesn't have experience, expertise, breadth in software.
That's I think we're exactly where I was hoping we would go on this. The folks who are in the early system design phase of programs, in other words, before contracts are even let out, tend to be pretty senior people like myself. And they have not been on the ground floor of building software today, because if they were, they would be more junior folks. So they don't necessarily know how the software is working and how a software architecture works and what the difficulties are, particularly with newer and newer systems. And this goes for not only the people who are doing, I would call their role as more of acquirers, but also for the systems engineers that they come and help them, who also tend to be senior. They don't necessarily understand if we break the system into these pieces versus those pieces, what are the benefits, pros and cons with respect to software. They would understand that, this particular thing would be better in wet weather for the hardware, and this one would be longer lifetime, and this one would be smaller, and this one would be cheaper. But with respect to the software, it's kind of throwing things up in the air. What we tend to do today is we say, you're going to build the satellite and all of the software that has to do with the satellite. You're going to build the ground station and all the software that has to do with the ground station, and you're going to build the handheld unit and all the software. What happens? Well, what happens is the software built for the handheld doesn't communicate well, rapidly, effectively, efficiently, ingeniously with the other software, and then the software's broken. And remember, the software is creating most of the new functionality, and most of the value of a new system is the software, and you have to allow for that software to be architected efficiently and well the first time if you want it to be able to do that effectively. Does that make sense?
It does. It does. You want to make sure that you're allocating functionality to the hardware and the software in a way that is optimal for the platform and not just one of those concerns independently.
And that sounds like a problem because we do need the satellite to have its software. And in particular, anything it needs to allocate power from the solar cells to the different units at different parts of the year, like eclipse or where it's colder or warmer. And we need the ground station to have its software work and the handheld to have whatever it needs to do work. But most importantly, we're forgetting that some of the software has to communicate all three together and has to make sure that each of the functions of the phone works with all the other functions. To use an example, it was given to me by our former CTO. They were looking at why it took so long to make certain computations on a battlefield system. And it turned out that 2 or 3 different contractors were involved in the process of this computation. And he said that when they looked into it, they found out that there was a Fourier transform back and forth between the frequency and time domains between this point and the beginning of the computation and the end of it 5 times. Nobody had decided what was going to be done in frequency domain versus time domain. So everybody got the data in from the last fave and said, oh, I have to switch it around, and did this computation, which not only slows it down, but as you know, it adds noise and adds a lot of uncertainty to it. So nobody had taken the software point of view up front, saying, what are the parameters that we have to settle on? What are the most important computations that are going to occur on each of these links? And how are we going to architect it so that we could get this parameter that we care very much about in terms of a quality attribute of the system, and we sacrifice this one, which we don't care so much about, because as you know from software architecture, it's all about setting these quality attributes. If you set it one way, you'll get these quality attributes over this one. If you set it another way, you'll get these. So the systems engineer has to know what they need out of the system in terms of what will make it function properly. But the software architect is the one who's up to speed on how software works, understands the changes that have occurred in cybersecurity, in software technology, in databases, whatever, and encryption, whatever, and understands what kinds of software architectures will provide those most needed and most important system attributes, and so that they can develop the software to prevent having computations take 5 different long steps when they could just be a pass-through or whatever it was that they needed for that computation.
Well, and this early engagement also helps us into that trade space where we are allocating functionality between software and hardware when we have a choice. Right? There are some things we can choose to do with the physical, in the physical realm, or in the software realm, and we have to make choices based on those quality attributes and system performance objectives about which implementation we're going to pursue.
Well, an example that came out in my work was we were looking at, say, a battlefield drone, and they let's suppose this one just takes a picture of the ground. It's simple. Remember, we couldn't do this 20 years ago, but today it's a simple drone, just takes pictures. And it has to bring that data back to the ground station. Now, does that drone include the functionality to encrypt that data or not? Because if it does, you've got a heavier drone, but you've got a smaller bandwidth, because the data that comes down is a smaller amount. And if the drone does not encrypt, then you've got raw data coming down, so it's a bigger bandwidth but a lighter drone. And all of these have to be traded off, including the fact that this is a battlefield situation, and if you've got raw data coming down unencrypted, the enemy is going to have as much access to the data as you are. Do you really want that? And including the fact that if it is encrypted, the people on the ground who are the good guys, us people, they have to have the proper security clearances to be in possession of and use the unencryption material, and that's heavy. They have to get it there as well. So there's a lot of considerations that go into it, and it could be that both options have to be carried up to a level at which point you can decide in this kind of situation you use this one, in that kind of situation you use the other one, and sometimes you don't know in advance how a war is going to proceed.
So we talked about having these conversations based on functional capabilities we want from the system and certain performance characteristics and the real-world conditions in which the system's going to operate. Now let's talk about sustainability, right? Keeping the platform, if you will, keeping the system alive as it is in operations and until we end-of-life it. You wrote in your blog post, if the software architecture is not modifiable, then the system as a whole may not be sustainable. Can you talk about the connections between architecture and sustainability?
Well, when I was a kid, a phone was this heavy thing made by AT&T and actually leased to the households. After a while, you could buy your own phone, but it was unbreakable. You could have 5 kids in your family, Mike. We could be hitting each other with a phone. Nothing was going to happen to that phone. It didn't need to be sustained. AT&T leased them out. You borrowed back the time and money to make phone calls. Nowadays, everybody buys their phone, but you know that things are going to change every night when you go to sleep. Facebook is going to have an update. And every app, every time I go look at my app store, I've got 13 things that need to be updated. And they're updated without my permission, but if I don't do it, they're not going to be cyber secure. And so I have to get them updated. And so the sustainability of the system, including that phone, has a lot to do with whether that software can be updated. It will have to be updated. It's very discouraging for people my age who are in senior levels, for example, of the government, to hear software is never finished. because they think of things as being like that AT&T phone. I can buy a phone. It will work from now until the day I'm done with it. Whereas today, with these extra high capabilities, things are changing. Our adversaries in warfare are coming up with capabilities that we have to then leapfrog over. And in order to do that, we have to be able to update the software. So in other words, in order to sustain the applicability of our new systems, we have to be able to update the software. So the software has to be, what was the word, adaptable?
Modifiable.
Modifiable, yeah, obviously, yeah.
Okay. So given all of the issues that we've talked about, when should software people first be involved when we're talking about a contract for a major systems acquisition? That's really up at the front, the very beginning that you're talking about, right?
In a sense it is. If I was a contractor like Boeing or Lockheed Martin or Raytheon or someone, I would think that that's the beginning of the program, but it's not. The beginning of the program is before, when we decide what we're going to put out that maybe Boeing or Lockheed Martin or Raytheon or Northrop or somebody is going to buy. Before the point where the contract is even awarded or let out in the beginning is the point where we just split it up. Okay, are we going to have somebody do all the software on, remember we were talking that satellite, or are we going to have some software allocated to a fourth contractor that has to do with linking all the other software together? How are you going to make this work? And of course, that's not easy either, because if you do have a software-only contractor and three hardware systems contractors, you know that software in the software-only contract part is going to have to interface with the handheld. It's going to have to interface with the software on the satellite. It's going to have to interface with the software on the ground station. And all those interfaces are going to be extremely difficult in the sense of having immense numbers of details and trade-offs. And somebody's got to do that work. If you don't do it early, you've got the unsustainable, unmaintainable, maybe you can patch it together software that we see frequently today. We see programs that are doing fine up until the point where they realize that their software is late. And it's late because you really can't write software if you don't know what you want it to do. And frequently you find out what you want it to do later after the hardware is at least in some degree of preparation. So it's not anybody's fault, it's just the way it works. And if you don't have software that's modifiable and the architecture set up for this situation that you're going to find yourself in, you're going to be having software problems. We have them today. We're going to keep having them. The best way to ensure that they will be minimized is to have that software architect be a required part of this early systems engineering team. And there's another reason why you can't just make it the same person, okay? Mm-hmm. Systems engineers have to be broad. They have to know about the Navy, and they have to know about technology, of lasers, and they have to know about the politics going on around this program in Washington. And there's so many things that a systems engineer has to know about. Whereas they excel, systems engineers, at the 50,000-foot level, and the interfaces, how do they all work together? The software people have to take a different tack. If anybody does, they have to do it, which is they have to be looking at the details. If you don't get your details right, you don't get working software. And furthermore, software is changing unreasonably quickly. And it will be even faster next year, not only in terms of the technologies that come up, but in terms of the things that we have to do to avoid cybersecurity problems. Used to be yearly, weekly, daily basis. Nowadays, it's like things could change in an hourly fashion. And so we have to make sure that the software architect is up to speed on that and continues to be up to speed while the systems engineer is looking broadly. I don't ever think that you're going to get somebody who has time to do both, much less be good at both.
Right, and we're talking about systems now with expected lifetimes of 50, 60 years for the capability, right? And we should not expect that the software is going to be the same actual lines of code 50 years from today. But we need to be able to architect platforms to be able to evolve the software as we continue to deliver the capability and sustain and upgrade the physical components over time.
Exactly. I think every time you make a change to the hardware, you run the risk of having to change the software to compensate and to make it work better. Every time you make a change to the software, You make a risk of having to change the hardware. Maybe it doesn't work with this new software. Maybe the hardware is old anyway, and now's the time to throw it. So the two are very tightly enmeshed in most programs and will continue to be. And you have to have both of those aspects well supported by people who know what they're doing. The systems engineers have their skills. The software architects have one that I believe needs to be brought in much earlier.
So can you tell me what's next for you?
Well, I'm retiring. Within about a month, I'll be sitting on the beach in Florida. Well, that'll be 2 months. But I think what I'm planning to do is to continue looking into systems engineering, because that's my initial love. And all this invaluable experience I've gained by working at the SEI on the software point of view and technologies and things. I hope to push it from the systems engineering point of view, and hope to be able to involve you and the rest of the SEI as well as we come up to places where we need both sets of skills.
I would very much like that. I've enjoyed the opportunity to work with you over the last number of years.
Back since you were a small girl, yes.
Yes. Well, thanks so much for joining me today. We'll include links to all of the resources we referenced in today's podcast in the transcript. Dr. Sheard's blog post is available on the SEI website at insights.sei.cmu.edu. You can click on the Browse by Author at the bottom of the page and search on her last name, which is spelled S-H-E-A-R-D. Thank you so much.
Thank you.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.